Hi everybody, this is Tom. I'm back in the shop today on a cold day in northeast Indiana. We're supposed to get a lot of snow tonight. And I've just spent the last couple hours getting the tractor ready for plowing. There's something about working outside in cold weather that, while it's uncomfortable, it makes me feel alive. Maybe because I'm so uncomfortable, possibly. Anyway, today I'm going to do a project just for fun. I had a viewer and longtime subscriber ask me about making a 127 tooth gear. And I think it's something he might be doing just for fun too. I'm not sure. But I started thinking about it, and you kind of come up against the fact that 127 teeth, 127 is a prime number, so it doesn't reduce very well, and doesn't lend itself to conventional kind of tooth at a time machining without either a direct indexing solution or a compound arrangement on a dividing head. Neither of those is particularly palatable. And I thought, well, I'll give it a go on the Hobbing machine. So what I'm going to do is take you through that process, and in the process, try to give a little bit of a refresher on index math, differential math, and try to maybe explain it a little better than I have in the past. I continue to get questions about that I haven't fully responded to really, so I'm going to try to do that in this video as well. So let's get started. Well, I had a long-time subscriber, Kenny. You know who you are, Kenny, who wanted to know more about making a 127 tooth gear for his closing lathe. And when people need a 127 tooth gear, it's almost always for the same thing. They're trying to make an English lathe turn metric threads. And that's a very cool thing, and it's a good idea. But 127 is a prime number, and that means that conventional dividing head math doesn't work very well. The dividing head math is 40 divided by 127. Most dividing heads are 40 to 1. And you can't really reduce that and calculate the holes in the circle and all that jazz. You can do it for 128, which gets you to 5 holes on a 16 circle, but 127 requires a compound indexing arrangement, which is an approximation, but it's a good approximation. But it requires a dividing head that's got a compound gear train with change gears and so on to accommodate that. And that's complicated. I mean, the dividing head that I have doesn't have that stuff. I could probably figure out how to build it, but man, that's a lot of messing around. However, I think with the differential setup on my Hobbing machine, I can cut a 127. And this is how that works. And I'm going to start and go all the way through the math for the benefit of anyone who might be interested. You know, please, if all you want to see is chips flying, there'll be some of that at the end when we try to cut this gear. The ratio, the index train ratio, the basic Hobbing relationship is 1 revolution of the work per Z revolutions of the hob. So Z is the number of teeth, and if all you had to do was move the work, that's what you would want, is 1 over Z. But now I use a 40 to 1 drive for my spindle, so that's 40 index revolutions to 1 work revolution. So I'm just going to substitute that in here, and I end up with a ratio equation that is 40 over Z. Now, let's skip over and talk about differentials a bit. You've seen me use this diagram before, where A is the input from the machine spindle, B is the output, and C is the drum. And we control that by putting a gear train between B and C so that these two are constrained to act together. I thought I'd try a little bit different diagram here, where A is an input, and we show that there's a sign to the rotation. So what we're talking about are rotations. So A is one of the inputs, or A is an input, B is an output, or A and B are both inputs and C is an output. But in my case, we're using A as an input, B as an output, and C is the control part of the differential, which is the drum. And each one of these things, I'm showing the positive rotation being counterclockwise, but that's just to distinguish positive from negative. So in some cases, like this case, we're going to want to set this up so that B and C rotate in opposite directions, because that gives you another whole set of solutions for the differential equation. Sorry, this isn't differential equations in the mathematical sense, but this is the equation of a differential. So the controlling equation is basically the rotation of C equals the rotation of A plus the rotation of B divided by 2. So what it does is a differential basically averages the two rotations of A and B. And if you solve that equation for A, you end up with 2C minus B. So that's kind of that's the fundamental relationship of a differential. Now, you grind all the way through there, and you divide both sides by B, and you get A over B equals 2 times C over B, and that's a ratio now of motion. So that can be a gear ratio, in fact. That's the way we're going to use it. Minus 1. And so B over A is just 1 over all that. So it's 1 over 2 times C over B minus 1. So we're going to use this equation right here to figure out what our gear ratio should be, because we need a C and we need a B that's going to give us the right A. That's how many times we want the spindle to rotate for the Hobbing machine. Now, in my machine, the way I've set it up is that B is always 21 for odd numbers and 20 for even numbers. And I should point out that if you subtract a negative B, that's equal to a positive B. So it's the same as adding. Sorry if that's too basic for some, but so in this case, if we pick C to be 53 and B to be minus 21, we get 2 times, if we use this equation right here, we get 2 times 53 minus 21, which is the same as plus 21. So this is 106 plus 21 equals 127. And that's our prime number gear that we're trying to make. Now, if we go back to the overall ratio description, that's 40 over Z. Now, if we just let Z equal A, because A is the number of revolutions that we want the hob to have, and Z is the number of teeth, so it's really just revolutions equals teeth. So we get 40 over A, and then I'm just going to multiply and divide by the same number. So it doesn't matter what it is, I can multiply and divide by that. So I get 40 over B times B over A. Now B over A is this equation right here. So this is what defines the ratio of the differential system. We really don't need to insert that into there because we're going to calculate B over A, or C over B based on this, and that gives us a value of B over A. So whenever we change C and B, we're going to get a different value for B over A and a different gear being cut. Now, let's go back to C over B, because we still have to set that up in the real world on the Hobbing machine with a set of gears. So that's 53 over 21. And with my machine, the bearings that I use in my change gears are too big to cut a 21 tooth gear. So I'm just going to multiply the numerator and denominator by 2, and I get 106 over 42. So my B becomes 42. And I'm going to, again, multiply and divide, because I have to break this down. I don't have a 106 tooth gear. So I'm going to multiply and divide by 60, and I get 106 over 60 times 60 over 42. This is exactly the same fraction as that. I've just multiplied and divided by 60. And when I break that down, 106 over 60 breaks down to 53 over 30. And then I've got 60 over 42. So these are two compounds. Normally in my differential train, I've only got one compound, but this is such a big number, it needs two compounds to deliver the ratio that I want. And again, because B is negative, all that means is that B and C have to rotate in opposite directions. So I'm not even worried about the sign here anymore, because I have a system on my machine that lets me switch the rotation of the output of the index train so that I get the correct rotation at the workpiece. So all I have to do to apply this relationship here is make sure that B and C are rotating in opposite directions. And when I do that with a single compound, I just add an idler, which reverses the rotation. In this case, I'm putting in two compounds, so I shouldn't have to do that. All I need is a 53 and 30 pair and a 60 and 42 pair. Now, when I tried to set this up, I've already done the work, but I'm going to try to explain it. Just the mechanics of that combination of gear numbers didn't work. These two pairs are too close in terms of their ratio, and I couldn't get it to work. But basically, one of the properties of fractions is I can switch the numerators or the denominators. And so what I actually put together is a set of compound gears that's 53 over 42. That's one set, and 60 over 30. These are both set up to speed up the rotation. Anyway, so that's kind of a walk through the math. So if I set up the differential this way, I get a B over A that is what I want for 127 teeth. And the only thing I have left to do is just correct the rotation for the B that I picked. Well, I'm just going to freeze this right there. And right where my finger is, if you imagine that says 21 instead of 42, that would actually be the right number. So I hope that's slightly less complicated than some of you may have imagined. And honestly, if this is not what you need out of this video, fast forward through it or wait for the next bit. Anyway, let's go down to the machine and I'll try to explain how I set it up, and then we'll watch it run. That's a really big blank. It's about 8¼ inches and 7/10 thick. I need to turn it down to 8 1/16, and then we'll put it on the machine and see if we've got 127 cuts, which is where we're supposed to be. Anyway, cool so far. Well, this is the double compound arrangement for the differential setup. I think you can kind of imagine why this might not have worked if I had the gears the way I originally had them set up. This one would have been smaller, and you end up trying to jam 2 sets of gears into mesh at the same time, and that's not ever going to work. But when I switched things around and started with the 30 and went to the 60, and then down here I've got the 42 and the 53, and that's driving this idler, which is driving the differential C gear, the drum gear. If you look at down in here, these are the coaxial shafts this is the A side of the differential, that's being driven by the spindle. This is the B side, that's the output. So this train here, which is way more complicated than it needs to be, is the output side of the differential. And then this gear down in here, that's just an idler with a shaft to take the motion through this plate here and deliver it to the differential change gears. So really all the action in this system takes place right here on this banjo plate. That's where the differential ratio is determined, and the rest of it is just kind of extra complication, I guess. This is about maybe a third of the way through. It's very slow because of the number of teeth on here. Slows everything down. But so far so good. It doesn't, I'm not hearing any signs of hard hits, but occasionally there's a little bit of a vibratory buzz, and you can hear the chatter of the cutting process. Well, that's just the way it is. That bell rings, that gear rings like a bell when they get that big. Well, just to wrap this up, you know I like to go for a happy ending. Said without innuendo. So here it is. This is the gear. (127 teeth). It's a big sucker. A lot of teeth too. I counted them twice, once on each side, just to make sure. Anyway, this gear looks pretty good to me. It meshes well. Life is good. Anyway, that's all for today. Thanks for watching. Thanks for subscribing. Thanks for your comments and likes. I really appreciate the fact that there are people out there that enjoy watching me do stuff. Thank you so much for your attention and your patience with me. And hopefully you'll get some value out of this video. But if not, remember there's always next time. Thanks. See you then. That's nice. That's very nice.